All right, team, here we go. And we're off and running. This is an example of floating point conversions done in Win32 And a bit of perspective and history on this. In 1984, the company out of New Orleans, CompuTrack, introduced a stock market analysis system. This was when the IBM PC first entered this scene, and this was at that point revolutionary because up till then such analysis was done on many mainframe computers and was restricted pretty much to the financial industry. So here at your fingertips you had a very robust broadly based financial analysis system. It also appealed to investors because it gave the pretense of having investment systems that were profitable. I'm not so sure that's correct. In fact, I'm sure that's not correct, but that was the lure. You could get systematic investment systems. As a result of that promise, it sold for $2,000 at that time, which is about $8,000 today. And because of its value, you actually had to open your computer and stick a circuit board inside that had a validation chip on it. So you actually had to modify the hardware of your computer to be able to run it, but it was extremely popular. And over the years, that data format, that CompuTrack data format, was adopted by essentially all the other consumer-level stock market programs. They all wanted to feast at the banquet that had been prepared by CompuTrack. And also, CompuTrack, about 8 or 10 years faded away, and 3 or 4 vendors took its place. It used a Microsoft 32-bit floating format, which is one of the key functions we're talking about today. I believe it was in what was called QBasic, and we'll examine that in detail. Here's an example of what you could see on the CompuTrack. This is somewhat a little bit later. The original, I believe, by my memory, was black and white, then went to color. At the top, you see a panel that has a weekly stock market, high, low, close, and then a smoothing as a red line in between. The lower 3 panels are different forms of analysis, high, lows, buy here, sell here, relative value, and so on. The successor after a couple of generations today is called MetaStock. It's out of Salt Lake City, Utah, owned by one of the major stock market financial companies. And it still uses that 1984 format for data compatibility. So files you generated back in 1984 will still operate today. And I have a database going back almost that far, back into the early 90s. So I've attempted to write applications for it using Systat, MATLAB, and R. The analyses that they do are so comprehensive that I've nearly never been able to approach what they do automatically online. It's kind of like trying to write your own Excel. So in doing these projects, I have written interfaces to those systems, and this required several floating point conversions. And now it's Win32's turn to do those. In order to do the diagnostic at a bit level, I wrote a simple word B dot, and this displays a 32-bit word in binary with the bits identified. The interesting part that does the work is in red, and this is our very familiar number conversion. S to D takes the single 32-bit number, expands it to 64 bits, and then the following sequence in red sets up a do loop that goes over 8 bytes at a time, 8 bits at over the 8 bytes, and it brings it out with into clustered groups of 4 bits at a time. So the equivalent down at the bottom of the screen in black. So I used this every time I wanted to look at a floating point number. I could bring it apart bit by bit using that little display. So here's a review of the,
real quick. Richard, are you really outside?
that's wonderful. Next, the QBasic Microsoft floating format. It's done from left to right, least significant bit on the right, going to most significant bit on the left. The exponent is the first 8 bits, shown in orange. Then the sign bit is 23rd, bit 23, which is the 24th bit. And then there's the hidden bit, which is pointed out to in green, which we'll talk about in a moment. And then the significand, which carries the magnitude of the number in 23 bits. In the earlier versions, this was called the mantissa. It was called the mantissa as a holdover from logarithm days. Current terminology called it the significand, as it's holding these significant bits. The purpose of that hidden bit is that the significand is always left justified with a 1 bit in the leftmost position. Since there's always a 1 bit in the leftmost position, no need to express it. So there's always an implied bit, 1 bit to the left of bit 22, except in the number case of 0, which we'll talk about later. So every time you reconstruct a floating point number, you extract the significand and then you insert that hidden bit. Here's the algorithm for converting this Microsoft QBasic format to IEEE. It looks pretty obvious when we go through it. It took me quite a number of experiments and tests and so on to work out the smooth process. The hill always looks less challenging after you've climbed it. The first thing we do is we extract the low 23 bits, which is over bit position 0 to 22, and then OR in 1 as that 24th hidden bit. This is then passed to the floating point stack, and in this case, Win32 is very useful because we are doing parts of the conversion in the integer stack and part in the floating point stack. Then in the floating point, we shift the decimal point 23 bits to the left because the exponent is given for the binary position. Next, we extract the exponent with a simple masking with a hex FF. Right shift that by 24 bits to bring it down to an integer relationship. There's a bias. The exponents are biased by the number 129, so it becomes a pseudo 2's complement number by offsetting it by 129. We then raise that bias to the power of 2. We take 2 to the power of the exponent using the floating point fourth F star star, which is the floating point exponentiation. Extract the sign bit and apply that to the final float. So here we go and look at the code. It's just as you would expect. The name of the word is MS to IEEE. First thing we do is we duplicate this number and on the data stack, and then mask out with that 7FFFFF, and then the ANDing with the 8, and that gets our significand. Then S to F moves it to the floating point stack. So there's our significand with the hidden bit restored. Then we do some exponentiation, put 2 on the floating point stack, 23 on the floating point stack, and then do a exponentiation and the right shift. The next step is to extract the exponent, which is done with the 0xFF, and then the right shift, minus 129 minus extracts the exponent. Then we scale by the floating point exponent, and finally we have preserved the original number. We go back and mask that bit signified by the 8, which is the 24th bit, I believe. And if that bit is set, then at the floating point stack, we negate the word. Again, as I said, it looks very obvious when we do it here. Working out, there's a fair amount of crunching and flailing around. Here's a couple of examples of use. The beginning one is that number, the hex number 0x85780000. That is the Microsoft floating point representation for the number 31. We pass it through our conversion routine, and then with an F dot we print it out. And sure enough, we see 31, which is printed by the Win32.4, and then that concluding 31.00 is from the quotation that's just above for checking purposes. The reason I use 31 is that in binary, of course, this is 4 5 ones. So this way I can see the present ones and then also identify where that missing hidden bit is. The next line is a fairly long number, and that comes out to be a date. That's in the Metastock format, or the Microsoft format for date, and that date is 1/23/0101. Now in the CompuTrack format, they ignored the century, so they only used the last 2 years of the date. This was fine up until year Y2K came along. Y2K came along, and all of a sudden their database is now obsolete, potentially obsolete. So for about 6 months there was gnashing of teeth within the industry on what are they going to do to resolve this. Their choice then was to put a century digit in front. So if you have a leading 1 in front, that means you're in century 2000, and if that is missing, you're in century 1900. The conversion is very simple. All you do is take the old format and add 19 to it, and that will get you to the proper 4-digit number sequence. So we see that whole input number is input. It's run through the MS to IEEE, and we get out 1/23/0101, which is 2023, January 1st. Let's look at the IEEE format. In this case, it's the one that's used in Win32.4 is a 64-bit format. The information is relatively similar, however, the arrangement is different. In this case, the sign is now the 64th bit at the extreme left end. The exponent is now 11 bits, and the bias is 1023, decimal 1023. Of course, the hidden bit is still there in position. It's in the 52nd bit position, and then the significand is a total of 52 bits. The pseudocode for this is sort of the one we saw before, but done in reverse. The first step is if the input, floating point input is 0, we then force the output value to be 0 and exit, and we're done. 0 is irregular in that there is no hidden bit. If we did a regular conversion on this, the conversion would try to force a 0, try to force a 1 as a hidden bit, which would give us a non-zero value. So every time a floating point number is processed, the first thing they do is check for 0 and handle it on an exceptional basis. Win32.4 provides a very, very interesting utility here. It allows you to transfer the image of a floating point number to the data stack. So on the floating point stack, we have a 64-bit 2-cell number, and word we'll see in a moment just transfers that image directly into the floating point stack, into the integer stack. This is done to interface to Windows. That number is passed to Windows because Windows uses the IEEE format, but they want it in a binary position. So once we have that on the data stack, we shift the low 32 bits, 29 bits to the right, doing a right fill, to the right, filling with zeros on the left. Then we swap the two 32-bit values, and now we're going to look at the high 32 bits. We extract the exponent with a simple mask. The 7FF extracts the exponent. 20-bit shift to the right brings our exponent down for calculation, and now we adjust for the bias. Now I show this as two adjustments. First we subtract the 1032 from IEEE, and then we add in the 129 for Microsoft. In reality, we only add in the difference between those two values. So that calculation only needs to be done once. Shift this exponent to the left. We're positioning it for inclusion. Extract the sign and then shift it 8 bits to the right. So you see now with these shifts left and right, we're positioning these bit arrays for the final ORing together. We extract the low 20 bits, shift the 3 of these left, which is needed, and then finally we OR together. So we have 3 elements on the data stack, and the significand, the exponent, and the sign. These are just ORed together to finish. And again, we see similar results as we saw before. The first line there is fdup F0 equals. We're doing a floating point check for 0. And if that is the case, we simply drop the floating point number, put 0 in the data stack, and exit. Otherwise, the FS to DS does the transfer. It transfers the 64-bit floating point number to the data stack as a 64-bit value. And then you see the other steps along the way. The shifting, extracting the exponent, we translate the exponent, position the exponent properly, process the sign, and then position the significand. Finally, OR it all together, and we've tidied up and have the Microsoft equivalent. This is a two-way test. This is the gold standard because we convert a number from IEEE to Microsoft, and then from Microsoft back to IEEE. And so since the calculations are quite independent, totally independent, is an extremely robust test. We start out in this case with a small number, decimal 0.00001. E indicates it's on the floating point stack. We translate that from IEEE to Microsoft, Microsoft to IEEE, bring it back, and then we with the F dots, we show the original value and the final value, and sure enough, they match up. As a test for negative numbers, again the same, we have a decimal 1, 2, 3, 4, 5, and it goes through the whole process, and again we get the same output. Very, very comforting when I saw that. This is an example of use. The upper window is taken directly from the stock market program. So this shows how it would appear within the host stock market program. The integers on the left, 1800 and so on, is a record number, and then we see the date, the stock market high, low, close, and volume. I read the same file, extracted it, passed it through these conversions, and then down below you see the format I've used is the year is 2023, the month is 6, and the day is 9, and then we see the high, low, close, and volume values. So again, comforting, we're getting the correct conversions for the dates and for the security values. And we're reading now, this is reading the original Metastock files in the Microsoft format. along the way, it occurred to me a nice little tool to have would be able to take a floating point number and just convert it to a scaled 32-bit integer, such as we're used to working with. A lot of times in Forth, instead of floating point, we use scaled integers, where we may scale an integer by 10, 100, 1,000, 100,000 to give us a wider range of calculation. It surprised me how simple this was. You can see at the bottom down there, we put the number 10 on the floating point stack. S to F takes our integer number to floating point. We then do a exponentiation of it, multiply the two together, which does the scaling, and then F to S brings it back to integer form. So we go to the floating point form to get the exponentiation and the scaling, and then back to integer form. And an example of usage of that, if we start out with in red, we see the 1, 2, 3, 4 decimal 5, 6, 7. E says it's a floating point number. 2 on the data stack says we want to scale by 2 decimal digits or 100. So we run it through that scaled number, and sure enough, we see 1, 2, 3, 4, 5, 6. So now we have a fourth integer that has been scaled by 100. So this could be useful in analysis. If I want to do more of my stock market financial analysis on the integer side, I can simply scale these security values. Most of the security values these days are expressed in pennies, so there are 2 decimal digits. So in summary, as I said before, for most of these problems, the solution looks a lot simpler after we're done. Along the way, there's a little bit of fog that comes along and alternatives, and I think I rewrote this about 3 times before I finally got it into the shape that I ended up with. And in the future analysis, I'll probably continue using some floating point and some integer, because things like shifting and masking are better done at integer, and some of the math is better done at floating point. Unfortunately, though, the mod and /mod do not exist in Win32 Forth, and to generate them, you're having to do a few subtleties in floating point, which I'm not sure I'm that capable on. So for some of the math, especially scaling with mod and /mod, it'll probably be done with the integer capabilities of Win32 Forth. So that summarizes this presentation. We've seen conversions from to and from Win32 Forth, and the technique, of course, is applicable to any other format you might run into. And next time I'll probably go into the file access and the reporting that I'm doing on this financial work. So do I have any questions or comments? Oh, let's see, references. All of this material today is on GitHub. So under GitHub, under my section, Bill Ragsdale, you can find the source code, and you can find a PDF of this talk. For reference on the formats themselves, this QBasic format is fairly obscure. It's what, now 40 years old. I was able to find it in a paperback book some years ago, a book on QBasic, but currently today it's available at this reference. You can see, and to get this, if you go to my GitHub page, you can download the PDF on this, and that will give you that'll give you that full format. And I'll try to copy this into the comment section later. But at that website, pcjs.org, 3 or 4 levels down, there is a summary of the QBasic language, the QBlang QBasic language, and the section 2212 gives several floating formats. So do we have any comments or questions?
You showed one note about testing. Was there any more extensive testing that you'd care to describe? I remember a certain Intel chip that had a floating point error or error in multiplication when something with like 6 nines and a 7. My memory fails me, but
Well,
floating point errors are always difficult to put salt on the tail of.
that's certainly correct. I'm not holding myself out as any expert on floating point. Um, I'm in pretty safe territory because we are just doing bit conversions, and the bits are very obvious when they. However, in floating point, there are range indications. There are some bit combinations for not a number, for exceeding highest possible number, lowest possible number, and so on. And we do not address any of those at all. I'm just pulling data from a very simple database, and they're all well within range. There are no challenges to the range values. So
I got a hoot out of the date expressed in floating point. As we all know, time and floating point don't mix. I cite the Patriot missile system as a great example. This ne'er-do-well that talks about autonomous vehicles. In his LinkedIn post, I think he mentioned somebody talking about money and using floating point. And I said, boy, there's an old fourther for you talking about integers and money. How's the book coming, Bill?
The book has had no progress in 30 days. My target was to complete a chapter a week, but I manage a amateur radio repeater that's up on a hilltop, and we've had about a month of headache on that, and so I have been doing ham radio heavily for the last month. Anyway, and some other activities. I share 5 hobbies, so anyway. But
we're so glad you have a life.
I'm teaching at the Magic Castle in Los Angeles. I teach a class on lockpicking. I've done it 23 times, 450 students, and we have a new class coming in preparation. So that's the most exotic of my hobbies. So I will. So
you don't.
Go ahead.
I'd just comment on floating point. I actually simply use floating point numbers for recording dates. I use integers, but I just use y, DD, and then for things that are time stamped, it's dot SS. But so, I mean, it throws away an awful lot of the interiors of available numbers, but it's a very simple format to work with, and it sorts correctly. So I find it a very convenient format. And I don't know, all the floating points, somebody who unfortunately is anonymous wrote a whole library for x86. That's one of the things, x87. So it's all, that's a problem with it. It's not something that can be moved from architecture to architecture.
You see this application today builds on my prior presentations on doing dates and date conversions. And in that case, I use a triplet. I use a year, month, day as 3 separate integers because Win32 has built in 3 dupe and 3 drop. So you can manipulate the year, month, and day as 3 separate integers and very conveniently duplicate them and drop them and shuffle them around. So anyway, with that, and
I have one more question here.
Go ahead with the question.
It was just a side comment. I appreciate your presentation, but I was just wondering, where are your headphones from? I really like them, and I'm looking for new headphones, and I was just wondering.
Um, I pause out of frustration because let's see if I can see the brand on them. I bought them 2 years ago. They work extremely well, cushioned with a mic on them and so on. Hold just a second. Well, the starting point is their Yamaha. So I did an online search and people talk very highly about the Yamaha headphones. So that's your starting point. And I'd like to welcome and acknowledge the presence of Chuck Moore. Hi there, Chuck. It's delightful to see you today. Thank you for being here and brightening up our presence. And so any further questions, we'll go back to Kevin.
All right, thank you. I'm very grateful for all of the things that that Bill has done for us, including presenting pretty much every frickin' month, Bill, along with all of its other activities and interests. All right. On that cheerful note, going forward, I see that the next agenda item. Any comments, questions, organization, business, side trips before we get into Brad's talk? All right, great. Brad, introduce yourself and on with the show. I can't hear Brad.